Hello.
Hello, sir. Good afternoon.
Hi, good afternoon.
Good afternoon.
Yeah, let's wait for some time. Let some people join, and if not, we'll interact. Let's wait for like 2, 3 minutes, and then we'll start our interaction session.
Yes, sir.
Okay, we can start discussing. So, do you have any questions, Satyam, or how is this? How things are going?
Yes, sir. It's perfectly, but I have some confusion in unit step, like Fourier transformation of unit step.
Okay. So, what's your confusion?
Could you explain, sir? I did not get the exact, the um, exact formulas and the graph, something like that. I did not
Okay.
get properly.
Okay. So, the first thing to note in the Fourier transform of the unit step function is that first unit step function is not absolutely integrable, right? So, which means that it does not even satisfy the uh, Dirichlet conditions. So, strictly speaking, the unit step function does not even have a Fourier transform according to Dirichlet conditions. But then, what we do is, in many cases where Dirichlet conditions are not satisfied, we can still write the Fourier transform with the help of this Dirac delta functions. So what we are going to do is we are going to use Dirac delta function to represent the Fourier transform of unit step function. Okay, so that's the first thing that we have to note. The second thing is that the unit step function, what we are going to do is we are going to express that as a limiting case of a sequence of functions. So let me share my screen. Can you see my screen?
Yes, sir.
Okay. So what we are going to do is, so we want to find out the Fourier transform of the unit step function, but then of course, like I said, that if you try to compute the Fourier transform directly, it does not exist because it's not absolutely integrable. So rather, what we are going to do is we are going to find out the Fourier transform of e power minus at u of t. Okay, so let us call this as some function x subscript a of t. So what does this mean? So given a value of a, you can plot a function here. So how does this function look like? So if you want to visualize how this function looks like, so this function would now look like, so this is time and this is x of a t. So for some value of a, it will look like this. Okay, so this is the maximum value that it can take. That's one. Okay, so this is uh, e power minus a t. So when time t equals 0, it's 1. Sorry. So this is not the graph. Okay. So this is a decaying function. So it'll look like this. Right. So as some let's say you're given some positive value of a. So this is of course for some a greater than 0. So given some value of a, so you have a graph which looks like this. So this is your function e power minus a t u of t. Now you keep changing the values of a. So you reduce the value of a. So as you reduce the value of a, what happens? You get another function like this. So eventually as a tends to 0, you will get just the u of t. So for every value of a, you get one signal here. And you call that signal as x of at. So basically, you change value of a, you get another signal. So what you can have now here is a sequence of a set of functions. So for each value of a, you have one function. Basically, you have a set of signals. And now you can try to find out the limit of this set of signals or the limit of the sequence of this set of signals. So for example, let's say if this a was equal to some 1 by n, then you can have x of 1 by 100, 1 by 101, 1 by 102, and so on, right? And as this n tends to infinity, a goes to 0. So now you have a sequence of functions, and you can try to find out the limit of this sequence of these functions. And that limit would be our step function here. Now, why is this useful to us? What we're going to exploit here is that each of this x of at, which is of this form e power minus at u of t, that has a Fourier transform. Okay, so because that has the Fourier transform, we are going to exploit that property, and then we can say that because every function in this sequence or every signal in this sequence has a Fourier transform, we'll say that the Fourier transform of the limit is equal to the limit of the Fourier transform of each and every element in this function. In other words, we'll say that limit, let's call x of 1 by n of t, n tends to infinity, this is equal to u of t. So what we are simply saying here is just apply Fourier transform on both sides. Now we'll simply say limit. We just take the Fourier transform of each of these functions and then apply the limit, and then simply say that that is equal to the Fourier transform of the unit step function. So basically the idea here is to construct a sequence of signals whose Fourier transform is known, and then take the limit of that Fourier transform in order to find the Fourier transform of the unit step function. This is the idea behind trying to find out the unit or finding the Fourier transform of the unit step function. And what is the Fourier transform of this sequence of functions? That is already known to us. So if you just find out the Fourier transform of e power minus at u of t, you will simply get 1 by j omega plus a. Okay? And all we have to do is just apply the limit a tends to 0, 1 by a plus j omega. Okay. So if you apply the limits to this, basically then you will be applying the limit to this. Basically what is here on the left hand side is exactly what is here. Now, if omega is not equal to 0, then applying the limit is very simple. Okay. So then applying the limit is just going to give you 1 by j omega when omega is not equal to 0. Okay. And that is the part that we have here. But when omega is equal to 0, you cannot directly apply the limit, because you will get here in the Fourier computation, in the Fourier transform computation itself, you will get some e power 0 term multiplied with 0 term. So it's like a 0 by 0 term or an infinity by 0 term, which is not defined. So when omega is equal to 0, you cannot apply this limit. You cannot find out this limit. So for the omega equal to 0 term is only the case where you have to worry. And by intuition, at omega equal to 0, you can simply say that, okay, this term goes to infinity. And for all other values of omega, this does not go to infinity. So you can model that simply with a delta function. Intuitively, you can simply say that. But when you write a delta function, the one thing that you have to note is that the area of the delta function, Dirac delta specifically, has a unit area. So in this case, when you integrate it back, so when you apply the integral back here on the right hand side, would you get back the integral of u of t? So that you have to check, right? Because otherwise there will be a mismatch in the area. So in order to find the area of the that we have here, what we do is we try to find out what will be the area of this function for different values of a and omega. It will so turn out that irrespective of the value of a, the area under this function is always a constant. Okay, and that area is pi. And hence we are simply going to scale this with pi. That's all. So the idea is, think of this as, like I said, a sequence of functions, and that function is some x of, and that function is some x a of t. The sequence of functions is converging to u of t. So this x a of t is converging to u of t. Okay, as a tends to 0. Now apply Fourier transform on both sides. So applying Fourier transform on both sides, you just take the Fourier transform inside the limit. Technically, there are conditions under which you can take the Fourier transform inside the limit. Here, it happens to be satisfied. So you take the Fourier transform inside the limit. When you take the Fourier transform inside the limit, this is what you get. Basically, this. So instead of applying Fourier transform directly, you apply Fourier transform to each and every constituent signal of the sequence. And then you let the limit being applied on the Fourier transform of each and every signal in the sequence. And that you claim is the Fourier transform of the unit step function. And that's how you get to the unit step function's Fourier transform. And finally, when you find the limit, what happens is, there are once again two cases. When the frequency is not 0, it's easy to apply the limit. But when the frequency is 0, you cannot directly apply the limit. What you do for that is, you find out what is the area under this function. Okay? So you find out the area under this function, that will turn out to be independent of a, and it is pi always. And hence, at omega equal to 0, you say that the value of the signal is equal to the value taken by the Dirac delta function, which is infinity. But when you integrate, the area does not go to 0. Sorry, the area does not go to infinity, but the area goes to a finite number, and that is pi. So does this help to understand why you get the Fourier transform of u of t to be something like this?
Yes, sir.
Yeah, the Fourier transform typically represents what it represents the amount of frequency components that is present. Okay, so let's get some intuition. So what are the frequency components that are present in the unit step function? So you have something like this. So if you for a moment ignore this part where there is a steep rise from 0 to 1, ignore that part. If you ignore that part, then what is the frequency component that is present? So that's the only frequency component that is present here is the DC component, right? And what is the energy of the DC component? It is existing from 0 to infinity. So if you try to find out the energy, it's going to exist like forever in time. So if you see its Fourier transform on the spectrum, you should see almost an infinite amplitude at the DC. And that is exactly what you're getting through this Dirac delta. Okay. But that is not the only frequency component that is present, because if I have a straight line like this, then of course I am supposed to see a delta. But I have a straight line only for the positive values of time. There is a sharp increase at 0. What does this mean? It means that there is a discontinuity, which means that within infinitesimally small time, I am moving from 0 to 1, which means the slope at that point is increasing from 0 to infinity, or almost close to infinity. So for this reason, we'll have infinitely many possible frequencies to be present at that particular time instant. So because at that time instant, we need infinitely many frequencies to combine together to give us a discontinuity, we'll have infinitely many frequencies. So that has to be incorporated somehow in the spectrum. And that is incorporated through this 1 by j omega term, which if you draw this 1 by j omega term, you will get something like this. So that will include infinitely many frequency components. So for the stable straight line, you get this Dirac delta. And for this one small discontinuity, you get this 1 by j omega. So maybe that might give us some intuition on why does the step function have a Fourier transform like this. Okay.
Yes, sir.
Okay. So how about others? How is everything going? So did you watch the lecture so far? Are things clear? Any comments, questions, feedback? So this week, the upcoming week is the last week of lectures, and I think the lectures are already uploaded, or if not, it will be uploaded by Monday. So this concludes the course. I'll really like to hear what you guys think. Any comments?
Sir, this is Gaurav here.
Yeah, hi.
Hello, am I audible?
Yes, yes, you're audible. Please go ahead.
Yeah. So this is a question in general as such. I am just thinking about the kind of job roles which where this signal and systems kind of analysis work um, is a is a major portion in the industry,
Okay.
across
So
industries maybe,
signals.
but uh,
Hmm. So signals and systems would be used under different engineering roles. I'm just going to focus only on electronics system design side. Even a mechanical engineer or an aeronautics engineer would use signals and system, but I'm not going to talk about that. Just for an electronic systems engineer, there could be two aspects where signals and systems could come into picture. One, if you are an circuit designer, let's say, for a circuit designer, signals and systems, Laplace transform and Fourier transforms are extremely important. So every circuit you would analyze would be through Laplace transforms or circuit or Fourier transforms. Let's say you're designing filters, then you would analyze the cutoff frequencies, everything through Fourier transform. Or if you're just generally constructing any circuit, then you would analyze the stability of the circuit, everything through Bode plots, which is all understanding of that comes completely from Laplace transform. So for a circuit engineer who is going to design circuits, Laplace transform is essential. You will not be able to design circuits without Laplace transform. So if you're designing circuits, if you're going to simulate circuits, then yeah, Laplace transform is essential. And to understand Laplace transform, of course, you need signal-in systems. The other aspect comes from, let's say you're a control systems engineer, where let's say you are designing drones and you are designing algorithms to control drones, or let's say you're even designing algorithms to control bikes or cars. So there is a lot of control system that goes in there. So there, a control system typically is once again analyzed using Laplace transforms and Fourier transform. So let's say you add feedback. So most of these control systems are designed through feedback mechanisms. And typically what happens is the addition of feedback can make the system completely unstable. It is very important that you analyze the system for stability when you add feedback, because easily feedback can make a system unstable. There are criteria to check the stability of the system when you add feedback to it, and that all comes from Laplace transforms. So in order to check if the criteria is met or it is not being met and all those things, you'll have to know Laplace transform. So the one statement that I made during the lecture, that all poles should be on the left half plane, is a very famous statement. That is one of the criteria that you will use if you're designing a control systems with feedback to ensure that the system is stable. So you will almost day in and day out use that rule to design feedback systems in control system design and so on. So it often appears in circuit analysis. If you want to debug circuits, once again, you'll need Laplace transforms. So these transforms are going to be essential for you guys when you are circuit designers or control system designers.
So, thanks for that bigger picture that you just shared with us. But just to get a better understanding or appreciate the role Fourier transforms and these kind of signals and systems techniques play, can you please shed
Hmm.
some light on its application in other industrial domains like aerodynamics or maybe biomedical engineering or
Yeah, sure. So but maybe I'll start with aerodynamics. So let's say you have an system, or you're designing a plane or something, and you want to analyze what happens to the drag of this. So typically what happens is, how do you design the body of a plane or anything? You would try to minimize the friction, or the what is called as the drag coefficient of the body of all these aeroplanes and everything. And how to compute that? It is typically computed by solving like several differential equations. And solving differential equations is extremely tricky if you just try to solve it as such. So what we'll do usually is we'll use Fourier transforms to solve the differential equations, to compute the drag coefficients, and to even optimize the design of flights and everything. All of it is finally modeled through differential equations, and those differential equations are extremely complicated. It's not simple differential equation. Those are differential equations in several variables, not just one variable, in several variables, and the order of derivatives will also be very high. So solving them is extremely difficult. Almost always, 99% of the scenarios, the solution is through Fourier transforms. So they take the Fourier transform of the aeronautics design, and then solution is computed through Fourier transforms, and then they take inverse Fourier transform and go back to the design. So almost every plane that you have ever seen in your life was designed using Fourier transforms. So the design there, basically in mechanical systems, most often, not just planes, any mechanical system that you try and devise where there is motion between multiple uh, layers of fluids, that is modeled through differential equations. So in a plane, there is a moving body and the fluid around it is air. So the interaction of this fluid on this rigid structure is modeled through differential equations. So that is a general physics thing. So wherever there is a body that is moving and there is a fluid medium around it, like even for example ships when they're moving or submarines when they're moving, the interaction of the medium around it is modeled through differential equations. And if you want to optimize the design of all these objects, then you need to solve these differential equations, and it becomes really, really tricky to solve them without Fourier transforms. So they use Fourier transforms to do this analysis. And in biomedical signal processing, especially what I personally know is I have seen in many scenarios where they use ECG and EEG, basically the cardiograms and the encephalograms, the brain waves. So these analysis, so if you just try to capture this signal from the multiple electrodes, so ECG typically has anywhere between 12 to 3 electrodes, and the encephalogram, the brainwave capture, it has anywhere between 8 to 128 electrodes. So you get so many signals, and it has several frequency components. So what happens is, if you want to detect arrhythmia and all those things, so they look for a particular low frequency signal. So you need to apply for filtering there in order to recover a particular frequency and look for particular frequencies to detect certain kinds of waves. For example, arrhythmia basically means that there is an irregular uh, heartbeat. So if there is an irregular heartbeat, your regular heartbeat follows a certain rhythm, which means there is a certain frequency component that is supposed to be always present. So if you get signals which are out of certain band of frequencies, which are not harmonics of your fundamental heart wave, then it corresponds to arrhythmia. So I personally known people who have implemented arrhythmia detectors through this technique. They have designed very robust filters, and the moment that filter detects a signal which is out of this band, they'll say that it is arrhythmia, and they show around 95% accuracy in this classification. So yeah, ECG, EEG, all these things use Fourier transforms and filter designs. So wherever you have to do some kind of frequency analysis, wherever your data is frequency dependent. So when I say frequency, it means some form of repetition of certain patterns. It's not necessarily a sine wave or a cos wave, as long as you think that there could be certain patterns which repeat over time, it means it's some kind of periodic signal. Not necessarily a periodic signal that is extending from minus infinity to infinity, but in certain duration it is periodic. All such signals could be analyzed effectively through Fourier transforms.
Okay.
And I am a communication engineer, telecommunications engineer. So all your Wi-Fi, your cell phones, everything, it is using Fourier transform. Like every single microsecond, it is performing a Fourier transform and an inverse Fourier transform. So all Wi-Fi and cell phone transmissions, they employ what is known as orthogonal frequency division multiplexing, which is basically implemented using Fourier transform. So every single microsecond, at least one Fourier transform is actually performed by your cell phone, and inverse Fourier transform is performed in order to communicate between your base station or your Wi-Fi router. All those things actually do Fourier transform. So if you're using your phone or laptop or connecting to Wi-Fi now, it means that your device that you're using is performing Fourier transforms to compute or to transmit your signal and receive your signal.
Mm. Well, yeah. Thank you. Thanks for that understanding that you just shared with us, especially the use cases across different domains and industries. Thank you, sir. I have another question,
No
which
problem.
is maybe very fundamental, maybe the one which we started off this course with. We talk about the signals being orthogonal time and again, and we have studied different techniques to find that out as well. But
Right.
I find it personally means to imagine or to conceptualize it difficult. I find it difficult. Means what does it mean when we say the two signals are orthogonal? Means as I understand, two vectors being orthogonal, that still makes sense to me because orthogonality means the one of the vectors doesn't have any component um, common to the another vector, other vector. So that being orthogonal. But when it comes to signals, how should one picture this? Means two signals being orthogonal.
So signals and vectors are not very different. So how would you represent analytically a vector? You would probably represent a three-dimensional vector like this, right? You will write an array x, y, and z, right? Or let me just say this is x1, x2, x3. So you can visualize, you can imagine when I give two vectors of this form and say that they're orthogonal. You can imagine, right? Now, what if I extend the
Yeah.
dimension of this vector? I can extend this to x5 and so on, right? So let's say I go up to some x infinity. If I give such two vectors and then say that they are orthogonal, are you still okay to imagine them?
Mm, yeah. So one vector hasn't got any component shared with another
Right. So
vector.
you
Like
would
like
simply
the
say that x transpose
projection
y equals
projection of
0.
it is,
Right. So
yeah,
if you are
yeah.
okay
That's
with
a
imagining
mathematical.
these kind of vectors, right? Now, if you have just three dimensions, then you can have axes like this, okay? And then you will say, okay, at this point here,
Yeah.
this is x1 comma x2 comma x3. You can visualize like this. Now, if I have like an infinite dimensional vector, how would I visualize this? So it becomes trickier to visualize this in axis and
Yeah.
space like this. So rather, what we can do is we can
Yeah.
visualize it like a single vector. You can just visualize a single vector. So I can just plot the first point here x1, second point here x2, third point here x3, and so on. So now you can visualize two different vectors just by plotting it in different uh, colors or something. So now here I visualized only one vector in this form. Now
Okay.
this is all because each element here is actually indexed by an integer. Now, what if you make this? What if you introduce one number between x1 and x2 and then keep introducing more numbers? Then effectively you will have one signal. So every signal that you can draw, in fact, is a vector, but it's an infinite dimensional vector. Does it help a little bit in imagination?
So time.
It is difficult to imagine.
No. I mean time being one of the axis. So amplitude will be on the other axis. So that makes it means I might be going in the wrong direction there, but x1, x2,
No,
x3
think of
will be
time as an
the
index.
magnitude of that signal at different times, right?
No, think of time as just an index. So think of this entire signal as a vector and think of time as just an index. So if I take this infinite dimensional vector here and say this x1, x2, x3, this 1, 2, 3 here are all like time. It's like an index
Okay,
to identify each and every value of or each and every coordinate of this vector.
okay.
Does it help in
So
imagination a little
for the
bit at least?
sake of simplicity, yeah. So can we work with just let's say four indexes or five indexes at this moment, and then if I have two signals
Hmm.
and I want to say that
Hmm.
these two signals are orthogonal, how should
Hmm.
I picture that?
So if you say that two signals are orthogonal, it simply means that you cannot scale one signal or combine it with different scaling factors and get another signal. That's all is,
Okay, okay,
uh, yeah.
okay. Yeah. So um, can you repeat your last sentence because I think that contains the crux of of this orthogonality
So
part.
basically,
So I
okay,
can't
yeah.
have
So
scaling factor.
So you don't have any component of one signal in the other. Let's say I have two signals X and Y. Now I
Okay.
cannot construct this signal X from Y in any manner. So there is no component of Y that is present in X and vice versa. There is no component of X that is present in Y. However I modify X, however I scale X, however I combine X in any many different ways, I should not be able to produce Y. If that is true,
And if the
then you can say
signals
that
are
they are
not
orthogonal.
ortho, if and what
If
would
they
be
are
the
not
other
orthogonal,
scenario if this in case the signals? Yeah, yeah.
yeah, if they're not orthogonal, it means that there is some component of X that you can produce from Y. So there is some component of Y that is present in X. Not necessarily the entire signal, not necessarily that X should be just simply some scaled version of Y. Not necessarily that. But there is some component. If you just take the inner product, X transpose Y, this is not equal to 0. Which means if you project that signal onto this Y, so you should be able to get some component of X. So basically this means that I can decompose X to be equal to some X1, X2 plus X3. And one of these components, like say, let us say X3, is just a scaled version of Y. Okay? And this C is not 0. Let us say if
Okay.
this is true, then this means that X and Y are not orthogonal. So there exists some
Okay.
component of Y.
Yeah,
In other
it
words,
makes
I
sense.
can just simply say that this is plus Cy.
Okay. Yeah, so this helps. Yeah.
Okay, good.
Mm, yeah, thank you. Yeah.
No problem. Yeah, any other questions? Not just questions, any comments, any feedback? I want to know how useful this course was to you guys, given that we are at the last week.
Well, that usability thing is only what I think. It's the course is very interesting. Personally, that's what I
Mm.
found, and it's quite
Mm.
consuming and demanding as well in terms of times and effort. But
Mm.
its applications and usability, I think we'll be able to appreciate that only down the line. Maybe once the control systems we study that part, that will be our first encounter. Maybe when we'll appreciate that we have learned so much in signals and systems.
Right. So when
Not
you
sure.
study
Means if
circuit
earlier
analysis
we, yeah.
and control systems, yeah, circuit analysis and control systems, and in both these courses, you will start using Laplace transforms left and right, and it will be useful. Yeah.
Laplace we did learn Laplace in our last term. So
Okay.
so that makes much sense. But Fourier transform, and especially means we have devoted uh, quite a major chunk of our time on pure analysis and systems and signals part besides Fourier as well. So I think we'll
So
only be able to
you might
appreciate
also
it
have
once
this
we
course,
start applying.
DSP. You'll have this course, digital signal processing, soon. So digital signal processing is going to use a lot of Fourier transform. So digital signal processing will help you design filters. So when you design filters, let's say you want to design a low pass filter or a band pass filter, and trust me, you will have to design filters for practical systems left and right. So which means you need to know how to design low pass filters, band pass filters, and high pass filters. And and the technique that you will need to design these filters are Fourier transforms basically. So when you study digital signal processing or circuit analysis or control systems, you will use all these concepts.
Mhm. Yeah. So one more thing, Professor, I did raise this question on the on the forums, and I did mention it in our last interaction as well. So you did give us some demo on the MATLAB code, but I
Hmm.
wonder if we can get access to the code that you made use of
I have uploaded the
in those
code. Have you
sessions.
not gotten the code yet?
No, I
Uh,
did raise a question on the forums, and I did mention it in one of the live sessions with TAs as well. I think it
is
was Jayanti
Jashwanti here?
ma'am,
Is Jashwanti here?
Jashwanti ma'am. Yeah. So
She's not here. Okay, because I've already
yeah. So
given the MATLAB code to them and I asked them to upload it. So it's still not accessible to you guys, is it?
no, we don't have the links. Rather, I we got the response that it might be proprietary or some kind of licensing issues why we
No,
still
no.
don't have
I,
access.
I have given them the MATLAB code long time back. Okay, if they have not uploaded it, I'll ask them to upload it.
Okay, yeah. So maybe we'll mention it again in our TA sessions. Um, you just want ma'am.
Yeah, because even just after I mean, I had uploaded even before our last interaction session, and I again sent them after our last interaction session. But if they have not still done it, I didn't know that they have not done it. Okay, I'll ask them to. I'll check with them and ensure that it's done in the next 1 or 2 days. So think of this course as more like an fundamental course, which where you study the basics, and you'll start using all these things in the upcoming courses like DSP, signals and signal processing, circuit analysis, and control systems. So I tried to include as much example as I could in the time that was available. So I had to trade off between the time that was available and the examples that I could give. So yeah, if I had to give more examples, then I would have not had enough time to cover the content. I think I already overshot the time that was given to me. Uh, I think this last week's lecture has more hours of lecture than what was allowed, and I wanted to cover some topics. Yeah, any other comments, questions? Also, I had shared the slides. Did you guys get the slides?
Uh,
No, sir.
Sorry, was that a yes or a no?
No, sir. No.
No, you've not gotten the slides yet. Okay, and ask them to send that as well. Okay. Mm. How was the quiz? Was it too difficult? Was it too easy, or was it okay?
It was okay, sir.
Okay, manageable. All right. Any other
I think
comments, feedback?
I think it yeah. So practice is the crux here. So in my case, especially, um,
Hmm.
I lagged. I didn't do much practice. That's why that's
Hmm.
why I didn't score well in quiz two especially. But the questions were what means I mean whatever was taught in the lectures and the assessments or assignments, questions were
Hmm.
pretty much in within that uh, were from that area only.
Hmm.
So it
Okay.
Yeah, that I agree, sir.
so if we
Practice
can
was not
expect
there.
yeah.
Hmm.
So
So
if we
one thing that
can
I would
expect
recommend.
our end term on similar lines, then yes, practice will be the will be the key. Yeah, and I hope
Yeah,
we'll
n term will
ensure
be like
that this
this.
time around we don't. Okay.
Yeah, please do. Yeah, please do practice for the n term. N term will just be like this. It will follow the same lines of your assignments, practice problems, and what we solve in the lectures. So because this is an online course, it's easier to just look at the lectures, and when you see the lectures, it would appear as if it's easy to solve problems, but yeah, when you're asked to solve it, and then there is no help around, like no books, nothing, it becomes slightly trickier. So
Yeah.
do one thing. So whenever you see a problem in the lecture, pause the video, think about it, try to solve it yourself, and see where till how much you can progress, and then again turn on the video, play it. Just get hints from the video. Don't play it till the end of the solution. Just play the video till you get what is the next step, and then from there try to solve it yourself, and then so on. That might help.
Okay.
So usually when
And
I teach here in
how
class,
much
what
will
I
be the
do is I
weightage?
do not. Yeah, let complete
Yeah,
with
go
it.
ahead,
So,
please.
so when I
Sorry.
teach here, I do not just directly write the solution on the board. Whenever there is a problem, I typically ask students to tell me what is the next step. And then when somebody tells me a wrong step, that's actually good for me, because now I can tell them why that is wrong and why they should not proceed in that manner. So an interactive session helps in especially problem solving, because I can correct their thought process, which is not present in the online class, but nevertheless, which you can try to imitate as much as possible. You pause, try to think by yourself, then try to proceed from there. If you can do that, that will be very
Sure.
helpful
Yeah.
for problem solving. Yeah, what were you asking?
So, about the weightage of questions from week 9 to 12 in end term, shall we expect more weightage to week 9, to the content covered in week 9 and 12 till 12,
Yes, yes.
or how will
Yeah.
that be distributed?
So probably around 30 to 40% of the questions will be from week 9 to 12. Yeah, you can
Okay.
expect 40% questions from that weeks.
Sure. Yeah. Thank you.
Yeah, no problem.
Sir,
Yeah.
how sir Fourier transform is different from Fourier series?
Okay. So the very first thing that in Fourier series that we want is we want to find out the frequency components of a periodic signal. If it is an aperiodic signal, then we use Fourier transform. So if you think about it, so let me just, what is Fourier series? So Fourier series is essentially nothing but you assume that there are only discrete number of frequencies that are present. So let's say you have a signal x of t, which is periodic. Then you say that it is periodic with some period t. Okay, which means there is a fundamental frequency, let us call that as some omega naught, which is equal to 2 pi by t. The sinusoids or the frequency components that are present in a periodic signal are always harmonics of this fundamental frequency. Whereas if this was an aperiodic signal, then it can contain all possible frequencies. That is, omega can be anywhere between minus infinity to plus infinity. So it can be anywhere between minus infinity to plus infinity. It can take any number. So frequency components of all possible frequency range can exist for an aperiodic signal. Whereas for a periodic signal of a given frequency, only the fundamental frequency and its harmonics will exist. So none of the other frequency components will exist. So this is the basic difference between Fourier series and Fourier transform. As you can see here, you can enumerate what are the frequency components that are present. You can say that omega naught, 2 omega naught, 3 omega naught, and so on. You can enumerate and construct a series here, right? So you construct a series of this form, or in this case, there is e power j k omega t. Okay, so you can construct a series where you add up all these harmonics and frequency components. If that is possible, then you say that it is Fourier series, and that is possible only for periodic signals. Whereas for an aperiodic signal, you cannot simply add up components like this because there are infinitely many components. They are not just these enumerations or the sequences that you have here. Here you can enumerate like 1, 2, 3, and so on. But the moment there are infinitely many, uncountably infinitely many frequency components, you cannot enumerate. For that, you have to integrate. And that is through what is known as the Fourier transform. So that's the fundamental difference between Fourier series and Fourier transform. So if you are given a periodic signal, then you can just use Fourier series. And if you're given a periodic signal, then you have to use Fourier transform. But Fourier transform is slightly more general. You can find out the Fourier transform of even periodic signals, but only problem is that you will have to use Dirac delta. So if you want to express even the frequency components of a periodic signal through Fourier transform, you can do that. So this is probably a slightly confusing part, but only thing is you will have to use Dirac deltas to represent it. So because Dirac delta representations are messy, we use Fourier series. Otherwise, we don't need Fourier series at all. Fourier transform is sufficient to represent the frequency components of both periodic and aperiodic signal. The only issue is because of Dirac deltas, we are using still Fourier series. Otherwise, you don't need to know Fourier series at all. If you are comfortable using Dirac deltas, then you can completely forget about Fourier series. Does this help, or still it is unclear?
No, sir, it's clear. And sir, what is a spectrum in Fourier transform?
So the spectrum is basically nothing but a visualization of all the frequency components that is present. So typically what we say is the spectrum is nothing but a plot of the frequency components versus the magnitude of the frequency component that is present in each of those signal XOT. That's all. So this is what we refer to as the spectrum. Let's say we have a cosine signal. If you try to plot the spectrum, you'll just see a pulse, an impulse at some omega naught and minus omega naught. So this is what we refer to as the spectrum. So basically, it is a visualization of different magnitude of the frequency components that are present inside a given signal. That's all.
Okay, then. Thank you.
Any other questions?
So even after we complete this course, how should we kind of keep practicing this? Like, should we take up the textbook and solve the problems one by one, or?
So one thing is, a lot of follow-up courses will anyway require Fourier transforms and Laplace transform. So if you're, let's say, taking a DSP course or a circuit analysis course, you will be using Fourier transforms and Laplace transform. So you will necessarily be practicing. So if you are taking a course which do not use this, then I would recommend solving exercise problems in textbooks. So I recommended, I think, the textbook that I was recommending was V.P. Lati. So that's a good book. Yeah. So this is the textbook that I would recommend. So you can just solve exercise problems from this book. And yeah, that's a good way to keep yourself in touch with the subject.
Okay, thank you.
Any other comments, questions? I would recommend, more than solving problems from textbooks, simulate things by yourself. If you can write a Python code or a MATLAB code where you can generate an arbitrary signal, compute its Fourier transform or compute its Laplace transform, and then if you can plot its pole zero plot, or if you can just plot its spectrum and then do some time scaling, time shifting, all these operations that you study, if you can simulate it, the implementation and simulation gives you much better understanding than simply solving, one or two problems from the textbook. So I would strongly recommend writing your own code in Python or MATLAB for every single concept that you studied.
Oh, so that means we don't have to manually do the Fourier transform. And
No, you can do manually the Fourier transform also. Of course, when you manually do the Fourier transform, you will not be able to do it for a large sequence because it takes a lot of computational power. You'll have to do it for a small sequence. So there is a small, okay, when you compute Fourier transforms in MATLAB, you can compute only for discrete signals, whereas we studied only for continuous time signals. There is a small gap in our understanding there. So you can use the inbuilt function itself. So probably in digital signal processing, you will understand the connection between discrete Fourier transform and continuous time Fourier transform. So yeah, Fourier series you can directly compute from whatever we have studied, but Fourier transform, slightly little more information is required to compute it in simulation than what we have studied, because we have studied only continuous time, and we can never simulate a continuous time system in any of the computer. We can simulate only discrete time systems. So that connection is still not discussed in the course. Maybe in digital signal processing it will be discussed. So yeah, for now you can just use the inbuilt function to compute the Fourier transform.
okay, okay.
Anything else?
Like you said earlier, it would have been quite useful if you had followed your offline procedure for some time, like once in a while. If you had like solved partial problems and allowed us to kind of interactively solve it.
But how would I do that in an online course?
Oh, okay, okay. Yeah. Very few students would. Yeah.
Yeah. See, actually, even now, there are only 6 of you who have logged in. Though I was told that I think 35 of you attended the quiz. So, whereas here we have only 6. The numbers, due to various reasons, I'm not going to complain this, but then people might be occupied at different points of time. So, it's very difficult to get the critical mass for an interactive class in an online course.
Yeah, yeah, agreed. Yeah.
So the last suggestion you gave about simulation and means trying this analysis out in MATLAB or Python kind of environment. I find that quite exciting, as well as like should be much more beneficial than just practicing problems from books.
Certainly.
So one thing which comes to my mind is if we can like frame a problem or create a small caselet or case study kind of thing and do it in this kind of environment like Python or a MATLAB kind of environment, and then that we submit as our maybe as a graded assignment or just as something which one can validate that yes, so that will add on to our understanding for sure.
So I can give an exercise.
What
that
I'm
is not at
suggesting
all
is that a
problem.
guidance means a step by step, means a bit of hand holding will be much appreciated on that front. The idea is really promising, but to start on my own working on this idea, I'll probably be spending quite a lot of time in searching net that what how should I start with the, let's say, Python, doing some signal analysis on that, and then what should be a real case that I should take up, and at the end of it, it should not just remain a coding exercise for me, rather I get to understand the concept I was behind.
Right. So this can be done, but I need to first understand how many people are comfortable with coding and what language they are comfortable in. Um, yeah, maybe I'll ask the TAs to first conduct a poll, try to find out who are all comfortable with Python. Um, yeah,
So
maybe
we
I'll
have a
do that.
Python course in this term, so a
But
basic
all of
Python
you,
understanding you can, yeah,
but
means
I don't know how many
whosoever
of you
is
are crediting
taking
that.
signals in system,
No, not all are taking.
whosoever is taking
Very
signals
few.
in system. Sorry, I
So
interrupted. Please
it
go
looks
ahead.
like, yeah, yeah, it looks like not all of you are crediting it.
Yes, sir. Not all are critical.
And maybe as a non-graded activity as well, some kind of work
That,
assignment,
yeah,
that
that
will
can be done.
certainly.
Yeah, that can be done. So I can give that. That should not be a problem. So I will send the code. Along with the code, well, I've already sent the code. So maybe I'll just send another assignment question along with that, with some hints on how to proceed.
Yeah, maybe some kind of Jupyter notebook kind of thing that will be.
Yeah.
I mean, I'm just thinking of format it can take or the shape it can take. So
Yeah.
that will help. Yeah.
Yeah, so the idea of me giving the MATLAB code was that you guys would just take the code and then change some parameters there and play with it and then do the same exercise. So that's what I was thinking
Yeah.
you
So
guys
that
would do, but I didn't know
we
that you guys didn't get
we
the
haven't
MATLAB
yet
code at
got
all.
access. Yeah.
Yeah, so yeah, I was actually planning for that, the same thing that you were saying, but yeah, looks like unfortunately you guys didn't get the code. So I will check with the TS again and then see why that was not done yet.
May I ask one more question? Like, in means what would be the like frontiers of this domain, like where the research is happening in signals and system in these days, or how is technology evolving when it comes to, let's say,
So
signals and systems?
now it has moved to a different kind of a framework. We use machine learning now. So if you see how we motivated Fourier transforms, Laplace transform was just an extension of Fourier transform. So how we motivated Fourier transform was that we wanted to express a given signal as a decomposition of some orthogonal vectors, right? And such a representation is
Yeah.
so powerful. It led us to so many different useful analysis. But this is just one choice of orthogonal vectors or signals. There could exist other choice of orthogonal vectors and signals, which could lead us to different kinds of analysis and different kinds of insights. So learning other kinds of these orthogonal bases is now the current research. And we do this now with the help of machine learning. And such kind of research is what is called as dictionary learning. So these kind of orthogonal bases together are put in a set that is called dictionary. So before this, it was done through what are known as wavelet analysis. I don't know if you guys have heard of this name, wavelet theory. Wavelet theory is an extension of Fourier analysis, where instead of just considering these complex sinusoids, basically phasors. So this entire course is running because of phasors. Now, can we think of other waveforms which are other than phasors? The first level of generalization is what is called as wavelets, where we use other kinds of waveforms instead of only phasors. And that was the research that was going on probably for the past 20 years or so. And after machine learning, we have moved off from wavelets. Now we are constructing our own generic basis, orthogonal basis. So if we pick images, we have different kinds of orthogonal basis there. For audios, we have different kind of orthogonal basis there. And depending upon what is your signal, we can construct our own basis, which is very useful for analysis of that particular signal alone. So if you want to, let's say, take an audio signal and you want to remove noise from that, so the noise will have a different representation, will have a different spectrum in that particular basis. So it becomes easier to filter out noise. So if you try to filter out noise only from Fourier analysis, it's slightly harder. But if you see latest noise cancelling headphones and all, they use machine learning because they actually decompose the signal in different bases, not necessarily in Fourier transform. Earlier, all these noise cancelling headphones, everything used to work on the basis of Fourier transform. They used to construct filters through Fourier design. But now it's all through machine learning because they have learned a different basis that is much better than phasers. But that will work only for audio. It will not work for anything else.
So that's like a machine learning algorithm in real time. Means the chip learns on the go when means what kind of
No.
noise signals are there around, and
Machine learning cannot happen real time in these things because the learning requires a lot of data. Like it requires huge amount of data, like sometimes even terabits of data. And learning typically happens offline, meaning the companies would collect all this data, and then they have huge cluster computers. From the cluster computers, they'll run algorithms on the cluster computers and learn from that. So what happens in real time is only these transforms. Once you've learned the basis, then you don't have to keep training your algorithm with that. You already know where to project, on what to project.
But
transformations are basically nothing but projections.
So what gets loaded into the chips are the pre-trained models.
Yes.
Okay.
But if you want an algorithm to work for a generic signal, let's say I just will design a small system that will work for both audio, will work both for audio and images, and for an arbitrary sensor, then still Fourier transform is unbeatable.
So certainly AI and ML looks like yeah. So I'll try to dig more on this part, and
Yeah, you can study
required, I'll
about what
seek
is
your
called
help
as dictionary.
on the line.
Yeah, sure.
What is?
What
Sorry,
is
what's the
dictionary
term
learning?
you use? And then okay,
It's
okay,
called
sure, yeah.
dictionary learning. Anything else from others? If there are not other questions, we can close. I hope you guys found the course useful. Thanks for listening to the lectures and coming for the session. And if there is anything, feel free to email me or discuss now.
Sure, sir.
Thank you very
Thanks
much,
for your
sir.
time.
The lectures were very, very, yeah. The lectures were very involved. Like, I think we would have to watch it again to kind of reinforce a lot of concepts.
Okay. I hope it was useful. Thank you.
Yeah. Thanks, sir.
Thank you,
It
sir.
was a meet, sir. Thank you.
Thanks.
Thank you, sir.
problem.